So thanks everybody for coming to NannoTalks. It's actually the last NannoTalks of this session before INA 18, that will be at the end of August, beginning of September. So today we are very lucky to have Catarina Guerrero with us, just to make a quick resume of Catarina's career. She has done a PhD on coccolith assemblages of Portugal. She then went to Bremen in Germany from 2015 to 2017, and she started to work with Caleb Bowman and sediment traps there. And then she came back to Lisbon in Portugal at the beginning with Marie Curie scholarship. And she has been working since then on the effect of dust on export production, and she's going to talk about that. But more recently, she is starting to work also on plankton sampling, I guess, in the Atlantic.
Yes.
So I will now give the end to Catarina for a talk. Thank you very much, Catarina.
Okay, thank you, Baptiste. Hello, everybody. It's a pleasure to be here. Thank you for this invitation. As Baptiste said, I'm a marine researcher working at MARE and IDEL, which are two research centers hosted at the Faculty of Sciences of the University of Lisbon. And I'm here to present some of our latest findings concerning the impact of atmospheric dust deposition on the export productivity and carbonate production by coccolithophore species in the tropical North Atlantic, and how this is likely to influence the biological carbon pump. This work was done closely in collaboration with Caleb Bowman, with whom I had the pleasure to work during my happy years at the University of Bremen, and also with Patricia Ziveri. Okay, so I guess I will start with explaining what is atmospheric mineral dust. So mineral dust basically consists of any solid particles with diameters smaller than 200 micron, which are produced from the resuspension of soil material by natural forces such as strong winds and or volcanic eruptions, for example. The particle size and the composition of dust are strongly dependent on the sedimentary sources that produce them. And they can include, for example, variable amounts of organic material, depending on whether they were formed in the proximity of regions of enhanced biomass burning. Now, the emission of dust to the atmosphere is something that can happen in all parts of our planet, as long as there is a combination between availability in easily erodible soil material and wind conditions persistent and strong enough to lift these particles off the ground and keep them in suspension. But of course, this combination is something that is very dependent on factors such as rainfall, vegetation, snow cover, etc. And that's why those really large dust plumes that you get to see from satellite images are usually produced in the most arid and semi-arid parts of our planet, specifically from the continental deserts. The magnitude of the winds driving the emission of dust also changes from small scale and short duration dust devils, such as these illustrated in these pictures, to continental scale dust storms, which can actually bring a lot of issues, both in terms of air traffic, but also for human health. Now, the main reason why we are so interested in understanding the dynamics of atmospheric mineral dust, it's because we know that there are megatons of these mineral particles being transported from the continental deserts for thousands of kilometers around the globe, transported by the winds, until they are deposited again, either on rainforests, on glaciers, on mountains, and of course also at the surface of the ocean. And we know that these massive amounts of dust particles carry substantial amounts of macronutrients and trace metals that are essential for fertilizing phytoplankton, and especially in those regions of the ocean at more tropical and subtropical latitudes where nutrient depletion results in low marine primary production during most of the year. Now, if you consider that marine phytoplankton contributes up to 50% of the total primary production in our planet, and thereby taking care of oxygen production and atmospheric CO2 sequestration, it's easy to imagine that dust deposition in the ocean is likely to become an increasingly more important alternative source of nutrients for fertilizing marine primary production in the context of the ongoing ocean warming. Now, in addition to acting as a source of fertilizing nutrients, dust particles also have this ability to promote the aggregation of carbon-enriched material produced by phytoplankton and zooplankton in the upper layers of the ocean. And by doing so, it increases its size and its density, and thereby facilitates its export and its further sequestration in deep sea sediments. So what this means is that either by acting as a source of nutrients and or as a source of mineral ballast, dust deposition in the ocean has an enormous potential to stimulate the biologically mediated sequestration of atmospheric CO2 and its subsequent export and sequestration to the deep sea sediments for longer periods of time, also known as the biological carbon pump. So this is pretty much at the basis of what we know as the iron hypothesis, which was first formulated by John Martin in 1990, when he argued that the input of iron by atmospheric dust deposition must have played a very important role in stimulating phytoplankton production in the past, resulting in a significant decrease in atmospheric CO2 during glacial times. So our research is pretty much directed at gaining evidence and insight into the effects of atmospheric dust deposition in phytoplankton production in the modern ocean. Now, of all the currently active sources of atmospheric dust, the Saharan Desert in the north of Africa is by far the most important, accounting for more than half of the total dust emissions on a global scale. Dust particles are typically transported by the trade winds in the form of these massive dust plumes extending all the way from the northwest of Africa towards the Americas, and occupying a latitudinal position which seasonally varies following the seasonal variations of the ITCZ across the tropical North Atlantic. And a recent study estimates that up to more than 200 megatons of these tiny mineral dust particles originating from Africa actually deposit across the tropical North Atlantic. So just to give you an idea of what this represents in terms of amount of dust, it would correspond to the weight of approximately 1.5 million blue whales. So we are really talking about a massive amount of Saharan dust depositing across this oligotrophic region every year. And even though we know that only a small portion of the nutrients that these dust particles carry are actually soluble enough to become bioavailable for phytoplankton uptake, we are still talking about the region of the global ocean that receives by far the largest dust fluxes on a global scale. So, of course, that dust deposition in this oligotrophic area is likely to have a role in the biological carbon pump. Now, existing evidence supporting the hypothesis of Saharan dust acting as a fertilizer are mostly concerning its ability to provide phosphorus in iron to stimulate nitrogen fixation by diazotroph marine cyanobacteria, which are among the most important phytoplankton organisms living in the tropical North Atlantic. And this is important because by stimulating nitrogen fixation, Saharan dust contributes to increase the nutrient stocks in this region, which then can fuel other phytoplankton groups living in this area. However, there is little evidence so far showing a clear ecological and direct response by other groups of phytoplankton to the input of dust. And that's pretty much what we have been exploring in the past few years. Now, the main reason why we are interested in investigating the response specifically by coccolithophores is that on one hand, we know that they include different species of distinct ecological preferences in terms of light and nutrient conditions, which can provide us with paleoecological and ecological information regarding the conditions of the upper photic zone of the ocean. And this includes, of course, nutrient deposition by atmospheric dust. So while as a group, coccolithophores are known to have a more oligotrophic affinity, because it's at tropical and subtropical areas that they reach their highest species diversity and where they contribute the most to the phytoplankton community. We know that they also include certain species of more opportunistic behavior that are known to respond very rapidly to short-term nutrient input, such as Emiliania huxley, and which we can monitor to explore changes in the nutrient input in the ocean by monitoring ecological changes in our observations, which can be potentially related to dust deposition. And the other reason is, of course, because coccolithophores are biogeochemically important. So on one hand, they act as natural sinks for atmospheric CO2 while performing photosynthesis to produce particulate organic carbon, or POC. At the same time, they act as natural sources of atmospheric CO2 while performing calcification to produce their cocospheres. And thirdly, they also provide a source of mineral ballast to, similarly to what I have explained to the dust particles, for increase the density of these carbon-enriched aggregates and thereby facilitate its export and subsequent sequestration in deep sea sediments, a mechanism known as the coccolith-ballasting effect. So what this means is that they both contribute to the biological carbon pump by which CO2 is removed from the atmosphere, but also to the carbonate counterpump through which CO2 is released back into the atmosphere. And to the ratio between these peak to POC fluxes in the ocean, which is called the rain ratio or the peak-POC ratio, it is largely what mediates the fluxes of CO2 between the upper ocean and the overlying atmosphere. And this ratio is important because the higher is the peak-POC ratio, the weaker will be the capacity of the biological carbon pump in sequestering CO2 from the atmosphere. So even though coccolithophores may not be as relevant compared to other phytoplankton groups in terms of POC fluxes, for example, diatoms, which are the big POC producers in the modern ocean, coccolithophores are among the most important producers and exporters of peak fluxes. And therefore, any changes in their productivity and or species composition related to dust-borne nutrient input in the ocean is, of course, likely to induce changes in the peak-POC ratio and subsequently in the efficiency of the biological carbon pump. So this is pretty much what we have been doing over the past few years. We have been chasing the effects of Saharan dust deposition on phytoplankton production across the tropical North Atlantic, and specifically focusing on the coccolithophore sinking assemblages across this region on the basis of a multi-proxy sediment trap study. Our study is based on a transatlantic transect of 4 sediment trap moorings between the northwest of Africa and the Caribbean, right underneath the largest dust plume originating from Africa. Traps M1, M2, and M4 located at comparably more open ocean conditions were collecting particle fluxes every 16 days synchronously for a period of 1 year. These traps were monitored by the Royal NEOS in the context of a larger project called Dust Traffic. And sediment trap CB was located slightly further northeast in the mesotrophic region offshore of the upwelling area of Cape Blanc in the coast of Mauritania. And even though it was also collecting fluxes for the same period, it was not synchronous to the other traps because it was being managed by a different group of researchers from the University of Bremen and from Marum in the context of the long-term monitoring program of Cape Blanc. So, of course, that in order to more accurately identify potential changes, biogeochemical changes related to variations in the dust fluxes across this region, we had to start by doing a very good or as good as possible characterization of the background tropical and oceanographic ecological conditions across this region. And this is precisely where I will start. So the first thing that we noticed was the presence of very striking transatlantic ecological gradients as evidenced by certain groups of species. We noticed a clear increase of surface-dwelling, fast-blooming species Emiliania huxley and Geophyrocaps oceanica towards the eastern part of the transect, and in parallel, a clear increase by lower photic zone species Florisfera profunda and Gladiolithus flabellatus in the exact opposite direction. And we also noticed that these basin scale ecological gradients were very nicely paralleled by increasingly warmer surface waters towards the western part of the transect and by increasingly cooler surface waters and higher chlorophyll A concentrations at the surface towards the direction of Africa. Now, we have interpreted these large basin scale ecological gradients as reflecting the response of coccolithophore communities to the geostrophic deepening of the thermocline from east to west across the tropical North Atlantic, forced by the trade winds in combination with the Coriolis effect. So what happens is that as the trade winds blow in westward direction across this region, they will force the surface water masses to flow in the same direction, leading them to pile up in the western part of the ocean basin and resulting in this east to west tilting of the thermocline. And because we know that the nutricline is usually associated to the depth of the thermocline, the nutricline is also tilting in the same direction. And that's why we have more favorable conditions for the development of surface-dwelling coccolithophores in the eastern part of the transect, where the nutricline is shallower and where we know that ocean conditions are influenced by coastal upwelling off the coast of Africa, while deep-dwelling coccolithophores, of course, will preferably develop in the western part of the basin, where the nutricline is deeper across our transect. Now, the second highlight from our work was that, quite unexpectedly, the highest total coccolith export production was not found at the easternmost part of the transect, where the nutricline was shallower, but rather in the exact opposite side of the ocean basin, where the nutricline, as I showed, was deeper across the transect. And in fact, the up to 3 to 5 times higher total coccolith fluxes found in the stratified western side M4 compared to the other traps were largely produced by deep-dwelling species Florisfera profunda and Gladiolithus flabellatus. So high fluxes produced by these species were not only compared to the other traps, but also compared to previous trap studies performed at higher latitudes in the North Atlantic, where fast-blooming Emiliania huxley often figures as the dominant species. And these transatlantic gradients were also reflected in terms of coccolith carbonate production across the transect, with site M4 also revealing the highest total coccolith carbonate fluxes across the transect, mostly produced by deep dwelling species in this highly stratified region. And this in turn resulted in higher coccolith percent contributions to the total carbonate flux, which were also recorded inside M4, and in turn resulting in higher PICIPOC ratios in the Western tropical North Atlantic. So our data showing how highly productive these deep dwelling coccolithophores can be in the context of heavily stratified tropical conditions, which have been projected to continuously expand in the future in response to ongoing ocean warming, clearly suggests that these species are likely to have an ecological advantage in the face of ocean warming. But while this might be a good news for their survival as a species, it's not such a good news for the climate of our planet, because their increase is likely to contribute to weaken the biological carbon pump through increasing the PICIPOC ratio in the ocean. Now, superimposed to these large-scale transatlantic ecological gradients, we notice the occurrence of two events of very striking increase in the fluxes produced by surface-dwelling, fast-blooming species Emiliania huxley and Gephyrocaps oceanica, also at the stratified site M4, and coinciding with enhanced fluxes of both POC and dust, and thereby pointing to the occurrence of dust-related enhanced productivity in the upper photic zone at the Western tropical North Atlantic. Now, the first event was during spring, when there was no precipitation and the trade winds were fairly strong, as typically happens when the ITCZ is still seasonally displaced towards close to the equator, and therefore not significantly influencing our transect. And it appears that during this time, combination between some degree of wind-forced steering of the water column with what we call dry dust deposition, which is when dust particles settle mainly by the force of gravity, appears to have resulted in very favorable conditions for opportunistic coccolithophore species to drastically increase in this region, and also of planktic foraminifera, which actually resulted in a very sharp increase in the fluxes of total carbonate. The second event occurred later in the fall, when precipitation rates were higher and winds were weaker compared to the spring conditions. And this was, of course, signaling the influence of the ITCZ over our transect, as typically happens during boreal fall, when the ITCZ seasonally migrates towards its northernmost position in the North Atlantic. And we also noticed the presence of a sea surface salinity minimum, which was also influencing ocean conditions at site M4 during this period, and which was signaling the presence of Amazon water, which had been retroflected into the north equatorial countercurrent, and therefore it was circulating counter to the wind into the open tropical Atlantic. So we interpret that the Amazon river plume was probably both providing nutrients, but also buoyancy for contributing to retain nutrients provided by atmospheric dust deposition at the uppermost part of the photic zone of the ocean, and therefore resulting in optimum conditions in terms of light, nutrients, and stability for several opportunistic groups to flourish during this period. So our observations indicate that combination between Amazon water inflow and what we call wet dust deposition, which is when dust is removed from the atmosphere with the help of precipitation, resulted in very good conditions for the striking increase, not only by opportunistic coccolithophores, but also by diatoms, as evidenced by the increase in the fluxes of biogenic silica and of chlorophyll A concentrations at the surface. Now, and what was interesting about these two dust-related events was that the PICIPOC ratio drastically decreased during their occurrence, which supports indeed the hypothesis that dust deposition, either by fueling productivity and or by acting as a source of mineral ballast, is likely to contribute to at least partially counterbalance the negative effects of the projected increase of ocean stratification and nutrient depletion. Now, when we investigated the efficiency in terms of coccolith-ballasting effect by these two main groups of species, we noticed that the correlations between the carbonate fluxes produced by lower photic zone coccolithophores and the fluxes of POC across the transect were relatively weak, suggesting that if these species do increase in the future due to being better adapted to ongoing ocean warming, they are further likely to weaken the biological carbon pump, also by reducing the efficiency of the coccolith-ballasting effect. Nevertheless, if dust outbreak events become more frequent in the future due to ongoing desertification of large areas in the north of Africa, dust is likely to counterbalance for this effect by stimulating species that revealed a higher efficiency in terms of the coccolith-ballasting effect, as evidenced by the relatively higher or relatively stronger correlation between the carbonate fluxes produced by Emiliania huxley and Gephyrocarps oceanica and the fluxes of POC across the transect. Now, as expected, the species revealing the highest carbonate mass, coccolith mass, were in fact the larger sized coccolithophore species, including Coccidiscus leptoporus and species within Helicosphaera spp. But when we investigated their potential role in terms of the coccolith-ballasting effect, we noticed that the correlation between the high coccolith carbonate fluxes produced by these species and the fluxes of POC across the transect were relatively weak, especially when comparing with the correlations revealed by the much smaller sized coccolithophore species, Emiliania huxley, which makes us question whether the coccolith-ballasting efficiency is less likely to be influenced by the amount of carbonate produced by a certain species, but rather by its ecological preferences, in the sense that species more prone to thrive in more productive conditions, where POC fluxes are higher, are apparently more likely to provide a more efficient effect in terms of mineral ballasting, which means that it seems that it is the POC flux that determines the coccolith ballasting efficiency rather than the other way around. We also compared the seasonal variations of the total coccolith carbonate fluxes across our transect with the concentrations of peak measured by satellite at the surface of the ocean. And we noticed that the only occasions where the two variation curves revealed a relatively good correspondence was at site CB, which is precisely located in the eastern end of our transect and where the nutricline is shallower. And also during the fall dust-related high productivity event, where peak also increased at the surface during that occurrence. So our data suggests that peak measured by satellite is likely to be a useful tool for investigating coccolithophore production by surface-dwelling coccolithophores, and in the context of regions where the nutricline is shallower, which is more likely to be the case along eastern boundary upwelling systems and at more dynamically mixed layered conditions at higher latitude regions, but not so much in the tropical and subtropical areas where coccolithophore production is mostly occurring at greater depths in the photic zone of the ocean, and thereby impossible to be detected by the satellite, because the satellite only has the capacity to measure productivity near the surface. And finally, our data also showed a clear, on one hand, a clear increase in the contribution of coccoliths to the total carbonate flux from east to west across our transect, which is somehow in line with the notion that coccolithophores are more important to the production and export of carbonate in typically heavily stratified tropical conditions. But still, the contributions were lower than expected. And this was especially the case in the easternmost sites, where coccolithophores only contributed 15% to the total carbonate flux, which on one hand suggests that other larger calcifying plankton species are likely to be more important carbonate contributors to the east of site M4. And on the other hand, it raises the question on whether our estimates are actually underestimating the real coccolith carbonate production, because we were using the morphometric method designed by Young and Ziveri, which mostly takes into account the carbonate of intact coccoliths, and therefore excluding coccolith-driven fragments, which are not included in our coccolith carbonate estimates, but still add to the total carbonate flux. So just to summarize all this information, our observations across the tropical North Atlantic revealed very striking ecological gradients in terms of coccolithophore species. Higher abundances or higher fluxes produced by surface-dwelling coccolithophores towards the east, and higher export fluxes by deep-dwelling coccolithophores towards the west reflects the response of these species to the geostrophic deepening of the nutricline from east to west across the tropical North Atlantic. Quite unexpectedly, the highest coccolith export production was noticed in the most heavily stratified ocean site M4, where the nutricline was deeper across the transect, and mostly due to the very high export production by deep-dwelling coccolithophores, which are likely to have an ecological advantage in the face of ocean warming. While this is good for their survival as a species, it's not so good for the climate, because they are likely to contribute to weaken the biological carbon pump, either by increasing the PICIPOC ratio and or by reducing the efficiency of the coccolith-ballasting effect. Nevertheless, if dust outbreak events become more frequent and or more intense in the future, they are likely to at least partially contribute to counterbalance the negative effects of ocean stratification by fueling phytoplankton productivity in the upper photic zone of the ocean, either in combination with wind-forced mixing of the water column during spring, or in combination with Amazon River inflow during the fall. This is likely to result in the stimulation of the biological carbon pump, either through decreasing the PICIPOC ratio and or through enhancing the efficiency of the coccolith-ballasting effect. Now, if you want to know more about these studies, you can check the papers which have been already published over the past couple of years. Of course, that as always in science, several questions remain open, and especially those related to the effects of atmospheric dust. And the first of which is, to which extent did Emiliania Huxley and Gephyrocaps oceanica increase by directly consuming nutrients supplied by dust, or indirectly by consuming nutrients made bioavailable by dust-stimulated productivity of nitrogen-fixing organisms. Also, is dust fertilization always pulsed, and therefore only benefiting species that are capable of responding rapidly to short-term nutrient input? Or can dust, which we know that is transported on a year-long basis across the tropical North Atlantic, also benefit more background tropical productivity and possibly benefiting species across the entire photic zone of the ocean? So these are questions that cannot be answered on the basis of sediment trap records. We would have to collect samples from the photic zone of the ocean and be lucky enough to collect them following a dust deposition event in the Atlantic. Also, is it the fact that we only saw evidences pointing to Saharan dust acting as a fertilizer at site M4, supporting an existing hypothesis, which is actively being discussed among the dust community, saying that the potential of fertilization by dust tends to increase with increasing distance to the dust sources. And this is likely to happen because the longer is the transport of the dust particles in the atmosphere, the longer its nutrients will be subjected to chemical processing at the level of the clouds, which will increase their solubility and therefore increase their bioavailability for phytoplankton uptake. So our data seem to at least partially be in line with this hypothesis, but of course we would need more information to be sure. And finally, when dealing with the regions closer to the dust sources, can we distinguish at all the different effects from dust fertilization of those from upwelling, which is a very important feature in this area? So as an attempt to address at least some of these questions, we have recently started, well, not so recently anymore, it was in late September 2020, a new project called Project Chase that aims to expand of this transatlantic source to sink perspective on the effects of dust in the marine environment towards a meridional perspective, taking into consideration the entire Atlantic in order to also investigate the effect of other sources of dust in addition to the Saharan Desert. So to that aim, we have been analyzing seawater samples collected across the entire photic zone during 2 expeditions of the Atlantic Meridional Transect, during which we were lucky to have observed the occurrence of several Saharan dust outbreak events, and therefore providing a very good opportunity to investigate what actually happened in the photic zone of the ocean during the occurrence of such events. So if you want to know more about this project or about these topics, you are most welcome to visit our website and to participate in our blog. And thank you for listening.
Thank you very much, Katarina. Oh, wait, I turn back the video. We had some very short cuts in, so I cut my video. So very great presentation. Thank you very much. Does anybody has a question? People are applauding. I'm pretty sure. Oh, I need also to check on YouTube. Let me check it there. Oh, we have comments. Oh, wait, it's okay. It's coming very fast. Let me just up. Is there? So we have a question from Yasu Wang. Is there a time lag between the dust storms and the corresponding coccolith numbers in the sediment traps?
I'm sorry, can you repeat the question?
Yes, it's also, I read it from the discussion, if you want to check it yourself. Is there a time lag between the dust storms and the corresponding coccolith numbers in the sediment traps?
I would need to understand what the person means by correspondence. I mean, we have an increase, a very clear increase in the fluxes of dust during these events, and such increases in the fluxes of dust coincide with a shift in the species composition of our coccolith sinking assemblages towards higher fluxes produced by fast blooming coccolithophores. And given that we are dealing with the western side M4, which is the region where the nutri-cline is deeper across our transect, and where coccolithophore sinking assemblages were largely dominated, actually quite overwhelmingly dominated by deep dwelling coccolithophores, this switch in species composition during these times of dust enhanced deposition is the argument that we represent as supporting the hypothesis of coccolithophore fertilization by dust deposition. I don't know if I was clear in answering your question.
If I understand well the question, I guess the question was on the time between the dust is coming and then there is the change. What is the time between these two?
Well, we are dealing with sediment trap records. So what we have is everything that has sinked all the way from the surface until being captured by the sediment trap for the period of 16 days. So we actually have the averaged signal of 16 days of export production, of dust deposition, of everything that is happening within the catchment area of the trap. So we are dealing with, I would say, a good enough resolution, but not good to the point that we can track the exact delay between the moment of dusts sinking in the ocean and the subsequent response of the coccolithophore communities. That is something that we are trying to explore now in the context of Project Chase, because during Project Chase, we are investigating photic zone samples, so samples of coccolithophore assemblages which were collected precisely during the moment of deposition of dust at the surface of the ocean. Hopefully, within a couple of months, I will be able to answer that question a bit better. But for now, I'm not really sure. What I can tell you is that at least within a period of 16 days, and taking into account that a dust outbreak event across the Atlantic usually takes about a week, I would say. I'm guessing that the response is pretty fast, but I cannot be sure for now.
Thank you. We have another question in the chat. Exactly, it says, how can we use this information that you just presented to us to track the impact of dust at the scale of kilo years? So I'll let you.
Okay. Well, I think that we need proxies for that, right? We already have from our records across the tropical Atlantic a good insight into the possibility of fast blooming coccolithophores increasing at the expense of dust deposition. So actually the ratio between the fluxes of fast blooming coccolithophores to the fluxes of the deep dwelling coccolithophores, this ratio was very nicely coinciding both with variations of SST by remote sensing, but also with variations of chlorophyll A and of dust deposition in the ocean. So we would have to use parameters to track the occurrence of dust deposition in the past, and we would connect those variations in time with variations, for example, in the ratio between these two major groups of coccolithophore species.
Thank you. Is there any other question, or you can, if you want, have comments also in the chat? I had actually comments on YouTube where a master student said that he really loved your presentation. It was a great opportunity for that person to learn a lot. So thank you for that.
That's great.
Any other question, comments? I have a question, but I'm not sure you have tracked that. Does this dust change the carbonate chemistry of the ocean at where it comes? Does it have an influence on the carbonate chemistry?
Well, it definitely changes the nutrient stocks in the ocean. So at least from that perspective, yes, it does. Other than that, I don't think I can really answer that. This is still a very new line of research. So the entire dust community, which includes chemicists, atmospheric researchers, and marine geologists and ecologists and so on, everybody is still trying to figure out how is it that the nutrients are actually released from the dust particles once they sink the surface of the ocean. So there are evidences that, for example, in the tropical northeast Atlantic, precisely underneath the region of highest outflow of Saharan dust, you have at greater depths and associated to an oxygen minimum zone, you have an anomaly of dissolved iron, which some studies indicate that are fueled by dust stimulated biological activity. So it's both recycled, it's from a recycling origin, but it's fueled by the very high dust fluxes at the surface. But this is still, I mean, it's very hard to find references, for example, showing biological responses by other groups of phytoplankton to dust. So most of those studies deal with mesocosm experiments, and on the basis of mesocosm experiments, dust seems to play a role, but for some reason it's not so easy to find those evidences in situ in the field. So this is pretty much something that we are still investigating on several fronts, let's say.
Okay, thank you. Is there any other question? Otherwise, I can ask another one. If you you said they were only 50% on the eastern part of your study, only 50% of the calcium carbonate that was from coccolithophores. Mm-hmm. But were you able to quantify what was the rest? Is it forams, theropods? Do you know the numbers of the others?
No. Okay. That part is still locked. We still haven't had access to the contribution by the other calcifying organisms. Okay. But most likely, yes. I mean, site CB, for example, there are previous studies indicating that pteropods can be important carbonate producers in that area, for example. But that part was not quantified yet for this transect. The data exists and can be used, but it hasn't yet. So hopefully it will be in the next few years, because I think we will gain a lot of insight about the contribution of all these different calcifiers for the total carbonate production in the tropical Atlantic.
Okay. We have another question from Yasu Wang, who asks, since dust is rich in iron, can we use iron content as a proxy for coccolith production?
Oof, that's a bit far-reaching, I would say. I don't think so. I would put it the other way around. If you have high coccolith production, maybe it's because you had higher input of nutrients, and that includes iron. Even though coccolithophores are not, for example, compared to diatoms, coccolithophores have less or lower requirements in terms of iron. So I would actually probably even link it more strongly to diatom production than coccolithophore production. Anyway, I would put it the other way around. So I think it's a bit too far-reaching to use concentrations of dissolved iron, or especially if you're not even specifying whether it is soluble or not soluble iron as a proxy for coccolithophore production. I think you would need a lot more of information to make that kind of inference, I would say.
Thank you very much. Okay, another question? No, let me check on YouTube too. But Patricia just left, so.
Oh, okay.
Okay, so I guess there is no more questions. Thank you very much, Katarina, for your brilliant presentation. It was a real pleasure to see your results. And as you mentioned at the end, if anybody wants to read more about that, you have published some, or most, or some of those recently, I guess. So really, really deep thank you. Just to make a short comment about something that has nothing to do with Katarina's or work or future work also, about no, not NannoTalks, actually about NannoTalks. That was the last one of this academic year. There won't be any more during this summer, and we still don't know yet if there will be in the future. It will be in discussion between the organizers, and probably during during INA. We'll see also see the comments from the community. If anything, I won't organize it anymore. It would be someone else, I guess, if it continues. More over on the INA 18, thank you for the ones registered for INA. Just to for the people that are coming, if they are interested in organizing a workshop, I sent today an email about that. So we are really short in time. So if you, in case you're interested, or you just want to discuss about this kind of event, possibly for INA 18, just mail me your comments, please. And that will be it for today. And you know that I will be probably sending you more emails in the next week. So if I have more comments to say. To conclude, I would like to thank you again, Katarina. And
you're welcome.
I wish you very good luck for your pursuing research on that topic. Thank you very much.
Thank you very much. Bye.
Goodbye, everybody. Thanks.